thank you everyone for tuning in. So I will be talking about how we use the beam to accelerate developing hardware for machine learning. So before I move on, I want to give a few special thanks. Sean Moriarty, who is the developer of the Axon library, contributed code that was used in this project. Ted Wong is a NX and Bumblebee contributor. He also contributed some code. Chris Ertel was kind enough to lend me his GPU rig, which made a lot of this possible. Alvin is my roommate, and without him, I wouldn't actually be here today due to some travel snafus. And Thomas Miller, who had some very important chats with me about LLMs and using LLMs. And all images that you'll see in this presentation are made with Sticker Baker, which is a project by Charlie Holtz, who works for Replicate, and he built Sticker Baker in Elixir I. So if you're interested in making images that look like the silly ones that I have in this presentation, go search Sticker Baker on Google. Okay, so a little bit about Positron, which is the company that I'm doing this work with. We are delivering hardware dedicated to LLM inference, both in workstation and blade configurations. So let's just say there are some competitive advantages over big GPU in that we are building inference-only machines, and big GPU has to satisfy both inference and machine learning training pipelines. And let's just say that for machine learning training, your bottleneck is literally just pushing flops through the machine, right? And what's interesting is for LLMs, when you have inference, memory bandwidth is the bottleneck. And so because big GPU has these competing interests, they are not necessarily building the most efficient processors for running LLMs. So because the Positron is focusing just on LLMs and just on inference, there's like a lot of architectural freedom to rethink the way things are done in computer chip hardware design. Okay, so given that background, I'm gonna do a quick outline of what I'm gonna talk about. The bulk of this is actually gonna be part 0. LLMs are not that much magic. I'm going to explain to you how LLMs work. Then 2 case studies, Beam Upstack, which is a LLM load balancer, which I wrote for Positron, and then Beam Downstack, which is actually using the Beam to probe and debug hardware. And then if I have time, we'll do part 3, which is what's missing from the Beam. And from my experiences, I have a couple gripes. Well, maybe like it would be nice if the Beam had this. Now, certainly we can do without them and did great without them, but I think our lives would be much better if these features existed in the Beam. And it's kind of opinionated. You may disagree with me, and that's totally fine. Okay, so part 0. LLMs are not that much magic. This funky little picture here is what Sticker Baker thinks matrix multiplication looks like. How do LLMs work? So, I don't imagine most of you have never tried an LLM, but the short story is that you provide an input, which is this like text on the left-hand side, and then it spits out one word, let's just say. We'll change that in a moment. What's going on under the hood is that the black box says, oh, I think the next word could be over, could be with, could be when, could be into, one of these two with these probabilities, and it just gives you the most likely one. You can also adjust settings so it doesn't necessarily do that, but usually this is what's going on. And then it will take that last token or word and then append it to the front and go once again. So you can imagine this is a pretty compute-intensive cycle. It's kind of like a tail call. As an aside, how does chat work? Probably most of you have interacted with an LLM in the chat mode. And the way that works is you've got this thing at the top that I have here in italics, which is a context. So you set this and say, hey, like this is who you are, LLM. And then you give a prompt, which is what you say. And then the LLM will respond with whatever it thinks should be the next thing. So based off of the combination of what you're telling it and what the context is, it gets a model of what it should be. And then what it literally does, but in order to do that, it literally generates usually, and it depends on the model, but this pseudo like weird like XML that's not really XML nonsense. But then but by doing that, that reduces to the previous case where you're just filling out text. So hopefully that gives you an insight into what's going on when you do chat. Okay, so back to this model. We're going to kind of unpack this and understand at a very high level what exactly is the math going on underneath the hood. So the first step is we can't really do math with text. That kind of doesn't make sense. I mean, I suppose you could use ASCII characters, but they actually tried that and it wasn't too efficient. The first thing we do is we do a step called tokenization, which is to break down your text into units of words. And they're not necessarily whole words. And these are designed, effectively you should think of this as like a compression scheme. So each of these is then assigned, and so sometimes you get like suffixes or prefixes, especially if they're repeated a lot. So it doesn't make sense to have a different token for jump and a different token for jump and jumped. But because ed is a pretty common suffix in English, for example, you can just reuse that as a token, and there might even be some semantic meaning that gets there that we can take advantage of. Then we take these tokens and we have just like a lookup table where it's, hey, these are these numbers. And then we do something called embedding, which is to turn these numbers using, again, a very simple lookup table into a really big vector. Now you see these dot, dot, dots here. That's an understatement. In Llama 7b, which is one of the smallest effective models, those dot, dot, dots are 4096. So that is 8 kilobytes of memory per vector per token. Just keep that in mind. There's a lot of memory going to be moving around. Okay, I call this semantic embedding because one thing to note is that these vectors kind of like are in, like, if you imagine sort of the linear space of all of these vectors, they have like these weird additive relationships. So the canonical example is that the vector between woman and queen is the same as the vector between man and king. So if you take the vector king, subtract the vector queen, that's the same vector as if you take the vector man and subtract the vector woman, for example. So embedded inside of these vectors is like some sense of meaning in a very large dimensional space. One step that I will not talk too much about is these vectors are also further tweaked by something called positional encoding, and that just changes the values depending on where they are in the sequence. Okay, great. So what do we do once we've got these vectorized? Well, the crazy thing is we effectively do what is a hash table lookup, okay? And so let's look at the next to the last vector here that I've bolded in black. We're going to generate a key from this. And this will make sense in a moment. How do we generate this key? Well, this is a 4096 vector, and this is a 4096 vector. So we have a giant 4096 by 4096 matrix that we have to do, multiply it against. Then from the same initial vector, we're going to create something called a value vector. Again, a huge matrix multiplication. And then what we're going to do is we're going to take the last token, and we're going to call this, and from this we're going to generate something called a query vector. And how do we generate that? Yet another giant matrix multiplication. So now we have these three vectors, query, key, and value, and I've labeled them that for a good reason. The way you should think about this is as if the query is like some term, right? And I'm just going to say, well, look, in the case of ed, maybe there's some, it's a suffix ed, gets encoded somehow, the fact that it's a suffix gets encoded in this vector here. Now our key that's created by the previous one has a part that is like, hey, I've got suffix ed in here, and the word jump is like a hash table with a bunch of different keys. If I present the suffix ed query against it, I'm going to get jumped, the idea of a past tense jump. And so the result of this transformation is going to be doing the hash table lookup of query against this jump concept. Does that make sense? Okay. Another way to think of this, which is maybe a little bit more accurate, is that the query presents, among other parts of this vector, a part that says, I'm trying to past tense the verb. And the key says, I'm a verb, and my past tense is jumped. That comes from the key value pair. Okay, and the key thing, the other important thing is that because this is such a huge vector, it's 4096, right? It can encode many, many, many of these different types of relationships that together can compose to create an idea of like the relationship between jump and ed, which should eventually create past tense jumped. Okay, then the next thing we're going to do is we're going to do this not just for the previous token, but for all of the tokens that came before it. So this is kind of like a weird pseudocode of what's going on here. Basically, we're going to go over all of the previous KVs, just do this query dot product, which is the mathematical operation that will encode the relationship between the query and the key. Trust me, this does basically a hash table lookup. We're going to apply a nonlinearity, which is not all that important, but you do need it for the math to work out. And then that's going to create a scalar, and the intensity of the scalar says how closely is this query and this dot related. If they're super related, which is what you would expect for a query and key, you're going to get a high value. And if they're not super related, you're going to get a low value. And that's how you can assign magnitudes of value, which is the resulting relationship between the query and the key. Okay, again, this is very, very simplified. This is not exactly the sort of thing that goes on. We're going to add up all of the relationships between the previous KVs and then do a transformation called feedforward, which basically allows us to sum up all of the relationships between ed and all of the previous values. Now, most of them in this case aren't going to be all that important, right? But, for example, Fox might say, oh, I see brown and I see quick before it. So maybe I can tweak my idea of Fox a little bit by both adjectives quick and brown. And how does the feedforward work? Well, that's just also a bunch of really big matrix multiplications. Finally, the last thing to understand is that there are multiple layers that happen. So we don't do this process just once. And the reason why is because that will allow us to accumulate more hierarchical information knowledge in our system. So before we just generated this one vector, what we will have done by the time that we've gotten to this point is we will have done it many times over each one of these. And then, hey, this matrix or this set of vectors looks kind of like this set of numbers. And guess what? We can do the same thing again and take jumped, and maybe we can relate that to quick brown fox, and then we can get some summed information of the whole context. So whatever vector comes out of the next layer is a lot of jumped, which we didn't know before in the previous layer, plus a little bit of quick brown fox, and then now we can create an understanding between jumped and quick brown fox. So we're building up layers of knowledge with each of these layers in the neural network of the machine learning algorithm. There are 32 layers in the simplest one, even more in the more complex ones, and even crazier tricks that people do for like ChatGPT 4. The last step is from the last layer, we get that one vector at the end. We just do a reverse lookup to find the token ID, and then we can convert that token ID to text. Okay? Does that make sense? Who got lost? All right, that's okay. Don't worry too much. You can review this on YouTube. All right, so the first part, use cases. Beam upstack. So this is a story of load balancing large language models. So remember, we had these huge pools of like numbers just sitting around. And guess what? Those might be able to be reused. And so let's figure out how we can maybe reuse that and why it might make sense to not just pull a off-the-shelf load balancer like HeyProxy or Nginx to do like a more intensive job. So our use case is that we're delivering hardware to customers, and we don't know what sort of deployment they might want. They might just buy one box like this, or they might buy an entire rack, and we would have to put like a load balancer in the top of the rack, or they may have a data center where the load balancer is located possibly even off-prem, maybe even in a cloud installation, who knows. So we want to support all these use cases, and of course, because load balancers need to be high availability, in a different sort of domain, error domain as the compute nodes. We want to use. We can use stuff like Erlang clustering to create like a robust, highly available system. And so this is why Elixir and Erlang are a good fit for building this sort of software, right? On top of just a standard load balancer, we want to just have a turnkey solution for our customers. So we want some extra functionality like API keys, token accounting stuff, and admin and A² features. It can certainly do that with HeyProxy, but for us to deliver a product that our customers are happy with, we want it to be like an entire system that is easy to maintain and easy to use, especially for some companies which are going to be not necessarily experts at like this sort of deployment. Okay, so why do LLMs need special load balancing? So when your user connects into the load balancing, first of all, your internet router might put you into any one of the load balancers. You don't know which one it's going to come to. But regardless of which one it goes to, we really, 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 really want that request to, if they are semantically similar, to be sent to the same machine. Because all of that context in that chat log that I showed you before is going to have to be recomputed if you land on a different node. If you land on the same node, it can be stored in the GPUs or hardware, and then you have no problem, because you can just skip a whole bunch of compute and then go straight to the new stuff and compute over the new stuff directly, right? So hopefully that made sense. So the tricky thing that we need to do is we want sticky internal routing. And so initially, we attempted to use GenStage. If you're at Sasha's talk, you heard him also have some struggles with GenStage. GenStage is a fantastic software for what you should, for the sort of things that it's designed for. But the basic general idea is to take an API request, handle it using the standard Phoenix plugs setup, push it into a request queue stage, send it in a tokenizer queue, and then the backends will route it to whatever hardware it needs to be, whether that's in a different machine somewhere else or if that's a hardware that's on the same machine. The reason why we wanted to have this be in a GenStage is because this is compute limited, and we wanted to only have as many compute nodes, any computes at the same time as there are, I guess, dirty NIF schedulers, if you know what that means. Moreover, the nice thing about our design was that if one of the subsequent queues was full up, we can send the request to another node, another load balancer on the cluster, and have it deliver content to the backend stages. It's especially important in the case if we have load balancers that are directly connected to the hardware itself. And we were able to use telemetry, which is, man, like I never used telemetry before I did this project, and it's fantastic in the Beam. Just, if you can, use telemetry. However, GenStage comes with a warning. If the data is uneven for long periods of time, then you may buffer excessive data from busy partitions for long periods of time. And so what that means is if you have any sort of heterogeneity in the consumers of any stage in the GenStage, you shouldn't be using it. And in our case, we may have like users overwhelmingly use one model versus another, and we are splitting our requests based on which model, because any given piece of hardware can only service one model at a time. So because of that, it turned out that GenStage was not a good choice, although we never really in practice ran into any of these problems in our initial set of testing. So just to be safe, though, we decided to just create a actually simpler engine where we didn't even use GenStages, but we did take the idea of demand from GenStages, and I rolled my own effectively demand processing system and simplified it. We I put the tokenizer into the request queue stage. So now we only have 2 hops. That's way less communication, so that inter-beam process communication, and so that lowers our latency for responses. Okay. So, okay. I'm going to do a demo. Feel free to go to chat.positron.ai, but please wait to prompt the LLM because it'll make what I'm about to show you a little bit confusing if you go ahead and shoot off right now. So don't do that quite yet, please. Let me see. How do I do this? Okay. So on the left is a front end that our CEO wrote. It's hosted on Vercel, and on the right is the admin is the admin for our load balancer. This load balancer is currently servicing 8 GPU nodes, so they're not our hardware yet, but it's capable. We're demonstrating the load balancing capability right now, and they're servicing 4 different models, and yeah, and so this just uses a standard OpenAI API contract to call into this, and this will forward it to whichever GPU nodes it is aware of and can handle it. So let's go ahead and give it a query. I'm going to query it with write me fizzbuzz in Erlang. And you can see that our node here is able to is seeing actively the communication between the front end, which is in Vercel. This is on a one CPU. This is a 1 CPU fly.io instance, and then over here, which you can't see, is a bunch of GPUs. It selected instruct-1 as the target, and it's doing token accounting. So tokens in 69, tokens out 262, and tokens per second for how long it took for this chat completion to go through. Okay, now feel free to start spamming with your quote, and we'll see if, we see some coming through. There we go. Looks like, So one of them crashed. Okay, so yep. So we're able to in parallel dispatch multiple requests to a bunch of different GPU nodes or machine learning processing nodes using load balancing software that we wrote in Elixir. Okay, let's go back to the talk. Oops. Okay, part 2, beam downstack. So this is to deliver the proof of concept that we can run LLM on this hardware. So up to the point of this, we had never successfully gotten a complete end-to-end run of any large language model on our hardware. So how do you test hardware in the beam? Well, you write a driver and you run beam as root. I was super scared to do this. I don't know why I was. I mean, like, it's a machine, like in our own private networks. Nothing's going to happen. But it was scary for reasons. You get like weird feelings and like So basically, the story is that you just load. Everything we're doing is in Linux, which makes things easier. We don't have to worry too much about handling weird side cases. But we use a NIF to load basically something in the sys directory. This is the device's memory region. Actually, Linux makes this surprisingly easy. Then you use mmap to map the device memory into local address space, save it into a resource so that it's properly GC managed, and then that's all you've got to do. Easy, right? It wouldn't be a talk by me if I didn't show a Zig language, but this is basically like a short skip through how you do this. If you use a different language, your mileage may vary, but basically you store the file descriptor, the address, the size, and offset. Then you create a beam resource, that encapsulates that, and a resource is a object that is garbage that is tied to the Erlang garbage collector. And then you have to define a destructor function, and the destructor does all the right things: memory, unmap, and close. So we're good citizens of the beam with this NIF. And then to use it, it's so funny. Like, this function name is open bar, which sounds like a joke, but it's called we call it bar memory, and I don't exactly know why. But basically, you open a file. You open a file descriptor, which is the path of the that you supply from that path that I showed you before, the sys directory path, and then you just run mmap, and then save all that into your resource, and then give that back to your beam stuff, and then everything, you just pass that thing around, and everything works out great. Easy, right? So we struggled a lot with doing this in Python. Eventually, we got it working in Python, and then it was extremely slow in Python to not mince words. One of the clear wins that we did was using the beam was super, super easy to lay out all of our giant 4096 by 4096 matrices in the memory layout that is required. In order to get extremely low latency, not low latency, extremely high throughput memory usage of piping these like giant matrices to the machinery that's going to do the matrix multiplication, we needed to scramble the memory layout into a highly optimized form. This is not representative, but it kind of gives you an idea of like what sort of things might happen. And like doing that in an imperative language where you're setting an array and then like changing like individual indices is really confusing. Guess what makes this really easy? I/O lists. You just write out exactly what you think it should be, and then you just send it, and it's like a contiguous binary. You're good to go. So I/O list. As a result of this, we by the fact that so the Python version just delivered the data to the memory row by row, and the Elixir version delivered it all at once by taking the I/O, turning it into a single binary, and uploading all that memory at once. We uncovered a concurrency bug in the hardware because we were able to deliver all of the data in one shot. That was something that we did not find in the Python implementation. So that was one clear win. A second clear win was unit testing with NX. So basically, the general idea is we load up a vector and a matrix, we test the matrix multiplication, and use NX as a ground truth for what that result should be. And so this is kind of a basic, this is code that comes straight from our unit testing, and basically remember that bar memory. So you pass that bar memory. Our system is codenamed Alderon. Bonus points if you can guess why we called it that. But basically, you just create an identity matrix, fill it with ones, and then load the matrix into Alderon. And then we also run a map mul. Then we expect as a result just the single matrix or single vector of a 4096 vector, and then we can assert that the expected result is the obtained result, right? So this case doesn't really have an NX matrix multiplication in it, just for space and when you multiply a vector times the identity matrix, you get the same vector back. But we were also able to do this with matrix multiplications with random matrices, matrix multiplications with matrices that we were able to instrument with whatever things we needed to find where in the chip the bug might have been. So if you think about that, think about that. And then the last clear win that we demonstrated was actually getting tokens out. So once I was able to demonstrate that we could do a dense matrix, remember all those stamped matrix multiplications? I was able to one by one swap in a CPU implementation of those matrices in NX for our hardware. And we did that with pattern matching. So the CPU implementation is here, and I cut that off because it's actually kind of complicated relative to the hardware version, ironically enough. But this is literally the code that takes a dense matrix from a vector that is supplied to a dense matrix and multiplied by a matrix that's stored in our hardware. And then, based off of this, we were able to verify that the full algorithm worked on our hardware. Okay, so as a result of this, I have a few opinions of what's missing from the beam to make these sorts of things easier. The first one is to do with NX. I think we should somehow, maybe this doesn't really fit in with how NX works. Maybe it needs a different library, but in-place matrix operations would be awesome. If we could somehow supply a destination set of memory that is overwritable, then that would be awesome. Isn't that mutable? Well, yeah, but guess what? A DB connection is, and so is an et stable, right? Same idea. Custom tensor kernels would be also nice. We can't currently JIT around custom functions in NX. And probably the big reason why that doesn't exist is because we need to communicate back to the NX compiler what the shape out is going to be. And also, you can't take a derivative. And again, NX heavily optimizes for training and makes, so it's in the same, I guess, bag as big GPU. It optimizes for training and compromises inference for that, which is not necessarily a problem, but it would be nice to have ways to do inference better anyways, because it's a bigger market. And the last thing that I really want is a common first-class NIF data type that is a resource bound to pointer and size. Currently, NIF interop is not easy. We have to use this special thing called dyn-call, which I don't think too many people actually use. But for example, this could allow GPU to DMA to do direct memory access to some region in custom hardware, which is our use case. But I'm also surprised that it doesn't exist for, say, allowing a GPU to write to like a NIC, because that's something that I'm sure some people in the Beam ecosystem use. As a bonus, I would love to see this work with something like an IO list for exactly the same reason, right? Okay, so having said all those things, it is still, Elixir is a fantastic platform for running machine learning infrastructure, and it is becoming increasingly convenient to run custom and common machine learning tasks in the Beam. And there are lots and lots of underappreciated features of this virtual machine that make really hard things like this really easy. And that's what I got.